Welcome to The Explainer. Today we're going to unpack a really fascinating question. We hear about artificial intelligence constantly, right? How it writes, how it codes, how it recognizes images, but how does an AI actually learn? Well, today we're popping open the hood to look right at the mathematical engine that drives that entire learning process. We're going to explore the incredibly dynamic world of optimization algorithms, tracing the journey from foundational gradient descent all the way up to the cutting-edge, memory-efficient matrix optimers that are powering today's massive language models.
Okay, let's dive into this. Behind every incredibly smart AI model is a surprisingly intuitive optimization process. You see, when an AI first starts out, it's essentially just making random guesses. It makes mistakes, a lot of them. But it uses a very specific mathematical strategy to learn from those exact mistakes, nudging its internal parameters step by step until its predictions actually align with reality. Here's our roadmap for the journey. 1. The machine learning landscape. 2. Finding the best path. 3. Obstacles in the terrain. 4. Momentum and adaptive learning. And finally, 5. The future of optimization.
Starting with Section 1, the machine learning landscape, understanding the terrain of AI. Because before we can understand how to optimize an AI, we need to clearly understand what it's actually trying to achieve in the first place. It really all comes down to the loss function. This is simply a mathematical function that measures how wrong the model is. For instance, if an AI predicts a house costs $50 but it actually costs $60, the error is 10. We often square that error to penalize the larger mistakes more heavily, a method known as mean squared error. The entire goal of AI training is just to make this loss number as small as mathematically possible. To really grasp how we minimize that loss, imagine you're standing on a super foggy mountain. You have no map, and you literally can't see the bottom of the valley. The only thing you can feel is the slope of the ground directly under your boots. Your goal is to reach the absolute lowest point. So what do? Well, you feel the slope and you take a step downward. You repeat this over and over until the ground is flat. This physical analogy perfectly describes gradient descent, which is the primary computational engine of modern AI. The mountain is our loss function, and our steps downhill are the algorithm actively adjusting the model's weights. That brings us to Section 2, finding the best path, strategies for stepping downhill. Our hiker has a few different strategies they can use to navigate down this mountain, and honestly, the math here is beautifully elegant.
Now, what's really interesting about this process is how we can break down complex calculus into 3 remarkably simple steps. First, we calculate the gradient. That's the derivative that tells us the slope's steepness in direction. Second, we multiply that gradient by a learning rate, just a small number that dictates our step size, so we don't accidentally leap too far and overshoot the valley. And third, we update the weights by actually taking that calculated step downhill.
But here's the catch. How much data should the AI look at before taking a single step? We essentially have 2 extremes. Batch gradient descent looks at the entire global dataset before taking one perfectly calculated step. It has extreme precision, but it's computationally intractable for huge datasets. It requires way too much memory and is painfully slow. On the flip side, we have stochastic gradient descent, or SGD. It computes just a single random data sample per step. So it's incredibly fast, but it's erratic. Because one single sample is a really noisy representation of all the data, the hiker kind of bounces around wildly on the way down.
If we compare these methods across 3 crucial metrics, data usage per step, training speed, and gradient accuracy, we see a classic dilemma. Batch gives you high accuracy, but very slow speed. SGD gives you fast speed, but low accuracy. The solution? That third row right there. Mini-batch gradient descent. It uses a randomized subset of data per step, maybe 32 or 256 samples. It's the perfect Goldilocks solution. It balances the data usage, maintains fast training speeds that are heavily optimized for parallel matrix operations on modern GPUs, and it provides a balanced, controlled noise gradient accuracy. This is absolutely the standard for modern deep learning.
Let's move right into Section 3, obstacles in the terrain, navigating treacherous landscapes. Because our foggy mountain is rarely a smooth, perfect bowl. It is completely full of treacherous hazards. The first major hazard is vanishing gradients. This happens when the slope becomes incredibly flat. The calculated steps become so tiny that learning just stalls entirely. The opposite hazard is exploding gradients, where the math compounds to create massive updates, causing the model's weights to wildly overshoot the valley and diverge into total chaos. And finally, we have saddle points. Just imagine the shape of a horse's saddle. It slopes up in one direction but down in another. As researchers Dauphin and his colleagues pointed out, the difficulty arises, in fact, not from local minima, but from saddle points, surrounded by a plateau of the same error, which makes it notoriously hard for SGD to escape. This really highlights that getting stuck on flat plateaus or saddle points is historically one of the hardest, most frustrating challenges in training deep neural networks. So, we need better tools. Let's look at Section 4, Momentum and Adaptive Learning, upgrading our hiking gear. And this brilliantly illustrates the solution, basic physics, specifically momentum. Instead of treating our algorithm like a hiker taking cautious individual steps, we treat it like a heavy ball rolling down a hill. By accumulating velocity from past gradients, the algorithm gathers enough momentum to just blast right through those flat saddle points and plateaus. Plus, it dampens those erratic, bouncy oscillations we saw with standard SGD. Enter the ADAM optimizer. ADAM quickly became the default heavy-duty tool for navigating complex loss landscapes. Why? Well, because it adapts the learning rate for each individual parameter. It brilliantly combines the momentum of past gradients with the running variance of squared gradients. It even applies bias correction to keep things super stable at the very start of training. And because of all these adaptive features, it requires far less manual tweaking by the engineers. But researchers noticed ADAM sometimes didn't generalize as well as older methods. The fix? ADAM-W. It tackles something called weight decay, which is a technique to prevent the AI from memorizing or overfitting data by penalizing large weights. Now, standard L2 regularization tries to do this by altering the loss function itself, but that actually interferes with ADAM's adaptive learning math. ADAM-W introduces decoupled weight decay. It explicitly shrinks the weights directly during the update step, completely bypassing the loss formula. It's a subtle mathematical distinction, sure, but a crucial one that unlocked way better performance. Finally, we reach Section 5, the future of optimization, scaling the frontier of LLMs. Because as we scale up to modern large language models, the massive LLMs powering today's AI chatbots, we hit entirely new walls, demanding entirely new paradigms. Take a look at this number, 2x. A new optimizer called Sophia actually achieves a massive 2x training speedup over ADAM on large language models. It does this by estimating the diagonal Hessian, which is really just a fancy mathematical way of saying it understands the curvature of the mountain perfectly. It adapts its step sizes dynamically based on exactly how steep or flat each specific dimension is, literally cutting training time in half. Let's move on and see how this builds upon our previous constraints. You see, ADAM is incredibly memory intensive. For every single parameter, it has to store running averages, duplicating massive memory redundancy across GPU clusters. At the scale of billions of parameters, optimizer memory actually becomes the dominant bottleneck. Modern methods like Galore and Sophia leverage brilliant math like low-rank gradient projections to drastically shrink that memory footprint while actually accelerating the model's convergence. And it's not just the optimizer formula itself, but how we schedule the learning rate over time. Take the cutting-edge WSD schedule, warm-up, stable, decay. It starts with a warm-up to suppress early chaos. Then a long, stable plateau allows the model to rapidly explore the deep river valleys of the loss landscape at a high learning rate. Finally, a sharp decay cooldown. This acts kind of like the Mpemba effect in statistical physics, where a rapid cooling mechanism forces the model's parameters to settle perfectly into their final optimal configurations. So the crucial point is this. From a single hiker taking cautious steps in the fog, to heavy momentum-driven balls, all the way to memory-compressed matrices mapping the curvature of high-dimensional space, the math of how machines learn is a constantly, rapidly evolving frontier. As our AI models scale to hundreds of billions of parameters, it leaves us with a massive question. Have we found the ultimate optimization algorithm, or is the next great breakthrough about to rewrite the mountain's rules all over again? Thank you so much for joining me on this explainer. I really hope you found this journey as fascinating as I do.